Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so I think we'll go ahead and get started. It's my pleasure to have Toby Grossman here today. I think most of you have met Toby before. He's been here as an intern and a previous MSR fellowship recipient. So I'm very happy to have him here. He's currently a PhD student working with Robin Balakrishnan at the University of Toronto. And Toby's done a pretty amazing breadth of stuff. And I'm looking at his map of his talk here. It's kind of a lot of cool stuff. Volumetric displays has been the focus of his thesis. How do you interact with true 3D data, which is kind of a topic close to my heart from my old PhD days. But he's also done sort of broad-ranging work in pointing techniques, really understanding at a fundamental level like how human pointing works and how you can model that. So he has sort of a wide swath of stuff he's going to talk to us about. So from there, I'll hand it over to Toby.
Thank you. So it's great to be back, but also be in a new place. This is my first time in the new building, so that's fun. I actually did just get my PhD on Monday. I defended successfully. Yeah, so so yeah, this is my first talk as a doctor, so it's going to be 10 times as good. Right? Yeah. So I'm going to talk to you about designing interactions based on understanding the capabilities of the humans that are associated with the technology. So to begin, a very brief overview of human-computer interaction. This is a slide you might see in an introductory course of HCI. And basically, you have three components. You have the human, you have the technology, and then you have the task. And the goal of the user interface designer is to come up with a user interface that allows the human to complete the task which they set out to do. Now, to understand exactly where the work I'll be showing you today falls within this framework, let's go into a bit more detail. So here on the left, we have our typical user according to Office clip art. And on the right, we have our typical technology. And what happens when we sit down and use our computers is we actually begin sending information to the systems. Okay, we actually begin communicating with the technology. And in almost all cases with modern computing, it's actually a two-way process. So the technology begins sending information back to the human. Okay? And hopefully through this process, the human can complete the task which they set out to do. Now, if there was a cable of infinite bandwidth connecting our brain to the technology, this would be a somewhat accurate depiction of what was happening when we're using our systems. But obviously, no such cable exists, and we need a user interface which mediates the communication between the human and the technology. And actually, everything on the right of this slide is part of that user interface. Right? It belongs down here. And what we're actually communicating with is where the processing is happening on the side of the technology, which in most cases is the CPU. Now, there's no cable connecting our brain to the CPU, but there is actually a direct and sometimes physical connection between our brain and the CPU, which you might not have thought about before. But for example, if I'm touching the spacebar on my laptop, the neurons in my brain are physically connected to my nervous system, to my muscles, to my fingertip, which is in physical contact with the spacebar, which in turn is connected through cables and sends a signal to the CPU. Now, despite the existence of this physical connection, it's of very low bandwidth. And with the example of the spacebar, it's just sending a signal of 1 bit, either on or off. Okay? And that results in a type of bottleneck in the information that's getting sent back and forth. And this is what I see as one of the main challenges in human-computer interaction, is the constraint on the information that can be sent back and forth. Now, this bottleneck has actually been discussed before. Rob Jacob talked about it in the early 90s. But what's interesting about it is there's two areas here. So this area here is the constraint of information being sent from the CPU to the human. The nature of this constraint is going to be determined in part by the perceptual capabilities of the human user. And similarly, this area here, the nature of this constraint is going to be determined by the motor capabilities of the human user. So to truly understand the problems with today's user interfaces and to understand how we should be designing for tomorrow's interfaces, it becomes important and relevant to understand these related perceptual and motor capabilities. Now, the nice thing about this framework is it not only gives us a way to look at today's user interfaces and typical technologies, which is what we have here, but it also applies to emerging technologies. So let's, for example, move to a high large resolution display or to an interactive tabletop display like Microsoft Surface. or a 3D volumetric display, which you'll see some research on later today. What you're doing when you change these technologies is you're changing what the associated perceptual and motor capabilities are with these systems. And it gives us sort of the building blocks to understand how we should be building user interfaces for these technologies. So the overall research approach, which I'll be talking about today and that I generally follow with my research, is to understand the low-level human factors associated with the interactive systems, applying this to both today's technologies but also tomorrow's technologies, and then using that understanding to design and guide the user interfaces and interaction techniques. And I'm going to begin by showing how we've applied this research methodology to one of the most fundamental interactions we carry out in today's graphical user interfaces, and that is selection. So selection has become so important because of the advent of the graphical user interface. This is an example of Adobe Illustrator. It's a great example because it shows how many selectable items could be within a user interface. And not only are there a ton of these selectable items, some of them can be extremely small. So if we look at these little slider widgets here, they're probably less than 8 pixels wide on the screen. So forget about a user with motor impairments. Just take a typical user. They're going to have difficulty selecting some of these targets. And because so many selections occur within any given usage period, it becomes important that selection is as efficient as possible. And based on what I was already saying today, we want to design the selection based on an understanding, in this case, of the motor capabilities of the human user. And fortunately, we do have an understanding, a theoretical understanding of motor capabilities when it comes to selection. And that comes in the forms of what's called Fitts' law. So Fitts' law is a predictive model which predicts movement times when selecting targets. So Fitts was actually a psychologist, and this model was developed in the 50s, where users selected targets either with their finger or with the stylus and measured the time it took to make these selections. And recently, when the graphical user interface did come out, HCI researchers realized they could apply Fitts' law to evaluating user interfaces and to evaluating input devices. So the law basically takes into account the distance required to travel to a target, which is A, and the width of the target. And it says the movement time is going to take on a linear relationship to the logarithm of the ratio between the distance and the width of the target. Now, the nice thing about this model is it tells us 2 ways that we can improve pointing in the virtual realm. So in the physical realm, there's nothing we can do about this. So if I want to grab my glass of water that's over there, I need to travel the distance to acquire it, and I need to grab it by its physical boundaries. But in the virtual world, there's no reason we need to follow this direct metaphor, which is generally what we do with the traditional cursor. And this law says we can do 2 things. We can either reduce A or we can increase W. And based on this equation that is well accepted, that will tell us we are going to make the pointing more efficient. Now, work in this area has been done before, and one of the original attempts was with area cursors. And what area cursors do is they basically increase W by making the cursor not a point, but this is the cursor here. It's an area. So to acquire a target, you just need to move the entire area over a point or over a target, which means you can now select really small targets. We came up with a new technique called the bubble cursor, which extends area cursors. So this was published at CHI in 2005. The problem with area cursors is that if you have multiple targets, like in the example of Adobe Illustrator, and you have a given area, when you cover an area, you might be covering multiple targets, and the system doesn't know which one it is that you want to select. So basically what the bubble cursor does is it allows the selections in both sparse and dense environments by using a dynamic activation region, which we'll talk about in a second. So the design, basically, we're diverging from traditional area cursors in 2 ways. One, we're changing the shape to circular. So the traditional area cursors were rectangular. And this guarantees that we're always capturing the closest target first, right? Just a property of circles. What's more important is that we are using a dynamic size. We basically are always adjusting the radius of the cursor such that we're only selecting one target at a time. So to do that, we use a fairly simple algorithm to adjust the radius. We consider the 2 closest targets, I being the closest target, j being the second closest target, and we define 2 distances. We define con_di, or the containment distance, the size the radius would need to be to completely contain the closest target I. And then we define int dj, the intersection distance, the size the radius would need to be to just intersect the second closest target. And then what we do is we set the cursor radius to the minimum of these 2 values. So in the first case, where con di is the smaller of the two values, we set the radius to that value and we're finished because we know we're completely containing that target and we're not even intersecting any other targets. In the case where int dj is the smaller of the two values, again, we set the cursor radius to that value, but we're not completely containing our closest target. So what we do is we just slightly morph the shape of the bubble to completely contain it, and thus giving the user good visual feedback that they have captured that target. So I'll show a brief live demo of the technique now. So the gray region is the bubble cursor. The black crosshair is just indicating to me where the center of the cursor is. And this is just a sample application where I can go around and click the red target. And you can see it becomes really easy for me to select targets that are really small, such as this one, because I don't need to place that crosshair on the target. I just need to approach it such that the bubble captures it. You can also see in these dense areas the bubble becomes much smaller to guarantee it doesn't intersect more than one target. Whereas in sparser areas such as these, the cursor can actually afford to become much bigger and sort of taking maximal advantage of void space. Then the last thing you'll notice is this morphing that occurs as I move from one target to another to guarantee that I don't intersect that second closest target until it becomes the closest target. So it's great to say, this seems to work well and it feels nice, but we want to know, is it actually going to improve movement times? Is it actually going to be beneficial to users? And we want to get a theoretical understanding of what's happening when I use the bubble cursor. And to understand that, we need to understand something called the effective width. So effective width is basically the width of the target required to activate it in motor space. And generally, the effective width is the same as the visual width with a traditional cursor. But with the bubble cursor, these two values are no longer consistent, because the motor space activation boundaries are bigger than the visual boundaries. And they're actually Voronoi regions. So a Voronoi tessellation of a screen is taking each point on the screen and putting a region around it such that any point on the screen, the closest target to that point is the target that's in the same Voronoi region. And when selecting targets with the bubble cursor, you're basically selecting the associated Voronoi region. So here the cursor, the crosshair is inside this region, which means this is the closest target, which means that's the one that's going to be selected. So the motor activation boundaries are the Voronoi regions themselves. So we want to know, can we model movement times to these targets by modeling the size of the Voronoi regions? So we actually performed an experiment where we wanted to see if we can model the bubble cursor with Fitts' law, where we use the size of the Voronoi regions as the width parameter in the equation. And we want to know, is the use of this effective width maximized? So here we have the equation ID as greater than or equal to the logarithm of A over EW plus 1, because we're saying we know it's not going to be any easier than selecting this region here, but it could be harder because of visual properties or whatever other causes. Okay. So what we did was we had a cursor, our bubble cursor, and this is just a one-dimensional task. So the crosshair was just constrained to the x-axis for control purposes. We varied the width of the target, and then we varied the effective width of the target by placing distractor targets around the goal. And along with the modeling, we also compared the movement times to traditional point cursor, so just your traditional operating system cursor, the point cursor. And we see that the bubble cursor did significantly reduce movement times, and actually significantly reduced movement times in all the conditions that we looked at. Okay, so this is looking at both width and effective width. So you see the difference is most drastic when we have a high effective width and small visual width. But even in the case where the effective width was only 8 pixels larger than the visual width, we're still getting an improvement. In terms of modeling, you can see that we get a really nice regression fit to the data with both the point cursor, which we knew would happen because it's just traditional Fitts' law, but also with the bubble cursor, where we're taking the effective width and plugging that into the Fitts' law equation. And when we combine the data together, we also get a nice R-squared value, which is showing that basically selecting a target with the bubble cursor is just as easy as selecting it with a traditional cursor, but selecting that surrounding area. Now, I mentioned we did this in 1D. We also repeated the experiment in 2D. I'm not going to go into the details because the results that we got were pretty much the exact same. You're still getting a nice regression value fit. So it's basically saying we can select targets with the bubble cursor as efficiently as selecting the surrounding area. It's saying we're taking maximal advantage of the void space. Yeah?
So it looked like that experiment doing a Voronoi which was square.
That's right.
Skinny. I mean, is it the width that's orthogonal to the direction of movement?
Right. And I'm actually going to get to this in a couple slides, but briefly I'll address it. The Fitts law equation is actually originally just a one-dimensional law. So when we moved to 2D, we tried to make the shape as regular as possible so that the Fitts law would still be applicable. So this is just for modeling purposes. So we did set distractor targets carefully so that we got a square shape region, and the length of the movement was always EW, effective width, in terms of the direction of movement. Yeah.
I'm trying to remember, when you did this with the point cursor, did you get feedback that they had entered into the effective width space?
With the bubble cursor? With the point cursor, well, with the point cursor,
You know you've entered into it because you get the bubble.
right. Well, with the point cursor, they actually had to select the target itself.
So there was no effective
Yeah,
width.
right. Yeah. So it was just traditional pointing, right? Okay, so these results are somewhat positive, right? It's saying, we have a technique that can improve pointing, but there are limitations. So here, if we take Minesweeper, which we're all probably familiar with, we can see, a limitation, right? And the limitation is that all the targets are completely tiled. There is no void space, so we're not going to actually improve pointing times. And actually, the very first time I gave this talk, Patrick was sitting in the front row because he was very interested, because he had a very similar technique. Yeah, that's right. And he actually put up his hand when I showed the slide, and he said, yeah, but as you progress through the game, you'd lose some of these targets. You get more void space, and you can actually select some of these targets a bit more efficiently. Another limitation with the bubble cursor is that you're always selecting a target. Okay, so by no means can the bubble cursor completely be a replacement to the traditional cursor. So for example, in a Word document, if I want to reposition the cursor, I do want to select void space. So if I want to position it before the word design, what might happen if I use the bubble cursor? Well, I'll probably grab onto this closest icon here, which I do not want to happen. Okay, so we need to take that into consideration. Potential applications are applications where I'm always going to be pointing at things, okay, such as browsing the web, where I'm always going to be selecting links. But another application is in user interfaces that have explicit selection modes. So if we go back to Adobe Illustrator, this is actually a user interface that already has explicit selection modes, that you select them from the toolbar, or from hitting a hotkey, you can transition quickly to them. And you're basically telling the system, I'm going to be selecting targets. So if the system knows this, there's no reason one of those selection modes could not be a bubble cursor mode. So the user can use the bubble cursor, make the selections that they need to make, and then transition back to whatever other tool they might be using. So to summarize what we did with the bubble cursor, we found a technique that significantly improves performance, and we were able to accurately model it using Fitts law. Now, as we've already talked about, there's a slight limitation in the modeling, and that is the Voronoi regions are going to be arbitrary shaped. And in the experiment we did, they were square shaped in the 2D experiment that we did. And as I mentioned, the reason that we did this was because Fitts law was actually just a one-dimensional law. It only takes into account the width of the target. So there was really no way to model these arbitrarily shaped Voronoi regions. Now, there has been some work in Fitts law extending it to 2D. So these are 3 different models that have been used in the past that look at the width and the height of the target. They all have slight limitations, but most importantly for us is that they're only, again, being applied to rectangular shaped targets. And again, we want to look at arbitrarily shaped targets now. Because with the bubble cursor, these Voronoi regions can be arbitrary shaped. And actually, this isn't only our only motivation for pointing at arbitrarily shaped targets, because we are starting to see some user interfaces that have arbitrarily shaped targets within their user interface. And as I was saying before, designers actually use Fitts law to evaluate their user interfaces at the design stage. And they cannot apply Fitts law to these types of user interfaces without making certain types of simplifications. So we have these 2 motivations for developing a new pointing law that can be applied to arbitrarily shaped targets. So we actually came up with a new law to model these types of movement times. And before I get into it, we'll talk about an analogy of throwing darts at a dartboard. So if I try to throw darts at the bullseye of the dartboard, and depending on my skill level, some might hit the bullseye, some will go further away. And if I just kept on doing this forever, eventually I'd form a distribution of hits. And from this distribution, I can now calculate the probability of hitting the bullseye with any single throw. And I could also calculate the probability of hitting any other target on the dartboard. I just shift the distribution over there, see what proportion of hits fall within that target, such as double 16. Or if I move to triple 20, the probability would go down because the region has become smaller. But if I was a more skilled player, or if I move closer to the dartboard, the compactness of the distribution would increase, it would become more dense, and the probability would raise. And we're actually going to apply the same idea to pointing. Before we do that, we need to understand two stages of pointing that occur. One is an open loop movement, and one is a closed loop movement. So the open loop movement is this initial ballistic movement that you take towards the target, where you're making no corrective movements, just this initial movement towards your goal. And with the open loop movement, you might end up before the target, you might end up overshooting, you might be lucky enough to hit the target immediately. After you complete this open loop stage, then your corrective movements start to kick in. And it's called now closed loop because there's a closed loop between the visual feedback and your motor movements. And you use these closed loop movements to actually end up on your target before you click it. So what we're going to do is we're going to apply this same idea of having a probability of hitting a target to this initial open loop movement phase of the pointing. So what happens with this open loop movement, when you move quickly to a target and try to click on it with no corrective movements, you actually form a normal distribution of hits. So we can now calculate the probability of hitting a target with this initial movement. And the key to the probabilistic model which we developed is that we take this probability of hitting the target with the open loop movement and map it to the index of difficulty of actually trying to click the target if you were using your closed loop movements as well. Okay, so we basically have a function that maps the probability to index of difficulty. And the nice thing about this equation is we can actually solve both sides of it. The left side is just the index of difficulty. This is just a 1D pointing task. So we know it's the well-accepted Fitts law equation, the log of A over W plus 1. But we also know the probability of hitting this target because we know we have a normal distribution. This has been found in previous work. So we can let x be a random variable under the normal distribution. And we're now basically calculating the probability of x falling within the boundaries of the target. The only extra thing we need to do is figure out what the standard deviation of this normal distribution is. And we found that it takes on a linear relationship to the distance of the target. So just like with a dart player, if you move further away from the dartboard, the distribution becomes more spread out. If you start from further away from the target, the distribution becomes more spread out. And we've actually done a study to find there is a linear relationship and solve for C, which is about 0.07. So we go one more step. We'll let theta be the cumulative normal distribution function. And we actually can now plug in values of A over W into both the left side and right side of the equation to start generating our function f. So if we plug in values of A over W on both sides, this is what we get for the function f. So we now have a function that maps probability to index of difficulty. And the second key to the probabilistic model is to say this function can be used for any pointing task. It doesn't matter if it's one-dimensional, two-dimensional, it doesn't matter what the shape of the target is. So now to apply this in 2 dimensions, we need to understand what's the probability of hitting the target. So we ran a study where we got users to make ballistic movements towards 2-dimensional points, and we captured the distribution of hits. Because by understanding the distribution of hits, we can understand the probabilities of hitting targets. So we're able to model these with bivariate normal distributions. So now the probability of hitting a target in 2D is basically looking at your region, which is defined by the target, and taking the proportion of hits that fall within that region. Again, just like throwing darts at the bullseye. Okay? And stated mathematically, it's the double integral of the bivariate normal distribution with respect to the region R, which is the shape of the target. So we actually ran an experiment in 2D. And what we did was we said we have this probability because when we ran the experiment, we knew what the target sizes were. Once we had the probabilities, we can go back to our function f and map them to the index of difficulty values. So when we did the experiment, we saw we got a really nice fit to the data, that we were able to predict movement times, map the index difficulties with a high R-squared value of 0.95. Now again, this is only for rectangular targets. We wanted to go to the next step. What about arbitrarily shaped targets? And the nice thing about this probabilistic model is that very few considerations need to be made when you move to the shape of a different target. The only thing that changes is R here in this equation. It's just what area are you integrating over. The one other thing you need to consider is where are you going to place the center of this target? Because as you change where you place the center, you're going to change the proportion of hits that fall within the region. Okay, so this is important. With a rectangle, maybe you'll just put it in the middle, but now if you have an arbitrary shape, it becomes important to figure out where the center of the target should be. So we came up with 3 possible methods of defining the center. One was just a geometrical method, basically averaging the vertices. It's called the centroid, or the center of mass of a polygon. And that just gives us a mathematical defined center of any polygon target. Another method we looked at was looking at what we call the selection center. So we actually get people to select a target from a certain point. This data assumes they were moving from the left, and see where they click and average those points to find the center. And this might be a more realistic value than a geometric center, but the drawback is you need all these people to make these selections before you can calculate it. And then the third method was an optimized method. So basically what I was saying is where you place the center is going to affect the probability of hitting the target. So let's place the center of the target on the point that would optimize your probability of hitting the target. The idea being that maybe humans are good at figuring out where they should be aiming. So if this is our 2-dimensional target, this graph shows x and y coordinates along with the associated probability if I was aiming for that point. And this is the same data in 2D using a gradient map. So the lightest point on this gradient map shows us where the optimal point to aim for would be. And what's interesting is actually this looks very similar to the selection center. And again, this data is assuming you are approaching from the left. So we took these 3 methods, and again, we performed an experiment. So we chose 10 shapes that all have various visual properties, and we got users to actually try to select it. So it was very similar to a Fitts law task, except the targets had arbitrarily shaped. So here are the results with respect to movement times. So this isn't extremely interesting, but what is interesting here is that we are seeing different movement times for each shape. So it is showing, yeah.
So were each shape's identical area?
What we did was we made each shape fit within the same bounding box.
They were different.
So the areas were different, yeah. Actually, the original paper that looked at modeling Fitts law in 2D used area as one of the metrics, and they found it didn't work very well. So controlling for area wouldn't necessarily control for...
I'm just curious.
Yeah.
Your function
Right.
actually.
Right.
depends on
Yeah.
this.
Do you want to comment on this, on the plus versus the minus shapes?
Right. Yeah, so the plus versus the minus, the plus sign is actually this height here, the height of the plus, was actually slightly less than the height here. What is interesting, and we have some more detailed data for the plus sign. Actually, why don't I go to the next slide? When I talk about the regression analysis, I'll revisit that. So we see we get good R-squared values again. So, and this is actually regardless of how we're defining a center. So it's showing the model is fairly robust regardless of how you choose the center. And here's the regression analysis presented on a graph. Now if we go back to the plus shape was actually shape number 3. Okay, so the triangle is representing the plus shape. And you can see that in almost all cases, it's actually higher than the regression line, which is showing not only were the times a bit higher because of its shape, but the times were even higher based on what we would have expected based on our model. So we actually looked at some of this data, trying to figure out why this happened. And when we looked at the data, we see a disproportionate number of points fall within just this horizontal region of the target. So people, when you have this target that's highly segmented, and the plus shape was really the only target that did have really visually distinguishable segments, users bias towards one of these segments. So what we think happened was that even if your initial ballistic movement took you to this point, the user, just because they're initially aiming for this part, might have moved down to this part anyway, which is might be why we get this slightly higher value than what we would have expected.
Because
hot eyes happening now horizontally?
I couldn't answer that question. There could be a number of reasons. The other reason could be that it would just be easier to select this part than this part. There have been studies that say a rectangle oriented this way is easier to select a rectangle oriented the other way.
You didn't have it right next.
Yeah.
No, we didn't do an X, but that would be an interesting follow-up.
You didn't log the mishits. Or you did.
Oh, the points of we would have logged those. I can't tell you exactly the distribution of those though. Yeah. The other thing we didn't look at is targets of extremely arbitrary shapes, and that's something for follow-up work. And actually, Patrick Bodish has done some work at looking at how do you visualize the Voronoi region when it's an extremely arbitrary shape. Because at that point, you really need to know what you should be doing and what area you should be heading for, especially for when you're using the bubble cursor when you don't even see these shapes. But this model really is ready to be applied. So if we have a user interface such as this with arbitrary shapes, we know where the cursor is coming from. We can take each region, plug it into the probabilistic model, and calculate our index of difficulties and get a sense of what targets are going to be easier and harder to select. If we go back to the bubble cursor, we can model movement times with the bubble cursor now as well. So if we just modeled this with a point cursor, the index of difficulties for these targets would all be very similar because we have the same width and just different distances, which is why the further targets have a slightly higher index of difficulty values. But if we switch to the bubble cursor, what we need to first do is do our Voronoi tessellation of the screen. And then we can plug these Voronoi regions into the probabilistic model and get our index of difficulty values. So one thing you might notice is that these index of difficulty values have lowered across the board. But the other thing is that they have much greater variation. And it's not the furthest target that's the most difficult target to select anymore. It's the one that's surrounded by the most targets, this target here in the center. So if we revisit the summary of the bubble cursor, we had this new technique that was improving performance, and we were able to model it with Fitts' law. There was a limitation in the modeling, and that led us to the probabilistic model. And this probabilistic model is not just only can be used for the bubble cursor, but for also any user interface with arbitrarily shaped targets. So at this point, I'd like to revisit the overall research approach that I was talking about before, and now shift from today's technologies to emerging technologies and how we're applying this methodology to new types of technologies. And the technology I'm going to talk to you about today is volumetric displays. And this has been the center of my dissertation research at University of Toronto. So volumetric displays are a new display platform which project imagery in true three-dimensional space. So it's not like a stereo system, which is basically tricking you into thinking you're seeing 3D. Points of light, or what are called voxels, are projected in true 3D. So viewing imagery on a volumetric display is just like viewing a physical object that's sitting right in front of you. So these displays really do have the potential to change the way we carry out 3D tasks. So you can imagine a doctor that's done an MRI scan and can now view that data in true 3 dimensions instead of looking at it slice by slice like they do today. Just to get a sense of the technology, this is the display we have in our lab. You have a flat projection screen, and when you turn it on, the projection screen spins, and it basically divides the volume into slices, but because it's spinning so quickly, you fuse all those slices together as a single 3D volume. I'm going to show a video now, so if we can get the lights dimmed. Nope, there's actually someone who, yeah. I apologize for the quality of video. It's a very difficult technology to video, but also the quality of the technology itself still has some way to go. Don't worry about as much the data that's inside there. But what's interesting about this video is that you see as you move from one viewpoint to another, you actually get the associated viewpoint that you should be having from that point. Okay? Just like in the physical world, if you move your head left and right, you see what you're seeing from a new perspective. So these displays are actually available now commercially. You could go out and buy one if you wanted to. And there are applications being written for them. Now the applications are very non-interactive. You basically do something on your computer, hit a button, and you see your 3D image on the volumetric display. What becomes really interesting is if we can use these volumetric displays in an interactive manner. So imagine the doctor not just taking an MRI scan and viewing it, but maybe starting to peel away layers or cutting away slices, zooming into interesting areas or labeling areas for another doctor to see. And that's when this technology becomes extremely interesting. So the work that I've been doing is investigating the interaction issues associated with volumetric displays. But again, we want to do this by first understanding the lower level questions, such as what are the perceptual capability questions, what are the motor capability questions associated with using a technology that is now doing everything in a third dimension. So this is the methodology we came up with. And before we get into these lower level questions, we want to just understand what the properties of the volumetric display is, because this will lead us to the important low level questions. So understanding the properties they have, also known as the affordances of the display. These are the four main affordances we identified. One, it's autostereoscopic. This means you don't need to wear any glasses, any head tracking hardware. It's basically ready and walk up and use. Another important thing is you're getting consistent depth information. And again, this is different from stereo displays, where there's a discrepancy in the depth cues that your brain is receiving, because the points of light are at one physical location, but you're perceiving them to be at a different location. With the volumetric display, because the light is actually there in true 3D space, the depth information you're receiving is consistent. These last two affordances are going to be interesting when we actually design interactions. We have a 360-degree view, which means one user could stand at one place and walk around and look at it from different points. But you can also have multiple users standing around the display, all seeing the display at the same time from different viewing locations. And then lastly, you have an enclosed volume, which means you can't reach in and grab things. So you can view things just like they're physical objects, but you can't interact with them like they're physical objects. And we're going to need to address this issue. So these affordances raise some interesting questions. We'll start with the perceptual side of things. So one is, we're seeing things in true 3D. The visual cues are now consistent. Is this actually going to improve our ability to perceive depth? So we ran a study where we compared volumetric displays to 3 other display technologies, one being a stereo system with head tracking. So that gave the user the motion parallax that you get with a volumetric display. As you move your head left and right, the scene would virtually rotate, so you get the perspective you should be getting from that viewpoint. And we also compared it to a stereo display without the head tracking, and then just the standard perspective display without stereo cues. We ran 3 tasks. The first was a depth ranking task, where a sphere floated above a floor, and markers were put on the floor to rank the different depths. And the user was asked to hit on the keyboard 1 to 9, depending on what depth they perceive that object to be. So obviously in 2D, this is a really difficult task. But for example, the answer here would be 3. The second task was a path tracing task. So now you have a dense graph of nodes and edges, and this is in 3D. And 2 of those nodes are going to be highlighted, and the user is asked, is a path of length 2 exist between these 2 nodes? So again, this is a task which is difficult in 2D, and the 3D cues allow you to better understand where these lines are all going. And if you're playing at home, the answer here is no, there's no path of length 2. And the last task was an animated task. It was collision judgment task. This is a task that's been used in air traffic control studies, where 2 objects fly together and they disappear at the last moment. And the user is asked, were these objects on a collision course or not? So a top view, which the user would not see, you can see the objects were either going to collide or one was going to go behind the other. So here are the results. We see for both the depth ranking task and the collision judgment task, the volumetric display did do better than the rest of the technologies, which is a good result. It's showing the volumetric display does have the potential to improve our perception of depth. Unfortunately, for the path tracing task, this is a task with a dense graph, the volumetric display did not do as good as the stereo display with head tracking. And we're fairly confident this was because of the quality issues of the display. So a lot of areas in the volumetric display are hard to see. You know, it's jittering. And when you really need to follow very carefully from one point to another along a line, any of those quality issues can really make the task a bit more difficult. Yep. Yep.
Was that a statistically significant difference? Does it look like the error bounds between?
Yeah, so this was weakly significant, so it was like 0.04, something like that. This one, it was not statistically significant. Yep. So this result is just as important as the previous one because it's saying the volumetric display has the potential to improve depth perception, but it's just not ready today, to put in the hands of that doctor because of these quality issues. And this type of study is going to need to be repeated in 10 years when the next, generation of displays comes out. Yep.
But the path tracing task does not even require any 3D perception, but you can answer that question in 2D.
Yes, you can answer it in 2D.
That would have done best would be one that was flat.
No, because, we're seeing here that the interface that was flat, that just perspective display, did not do as well. And there's previous studies by Colin Ware, who's an expert in information visualization. This is actually where we got the task from. And he's shown that 3D cues actually aid your ability to complete this task. So let's look at one other perceptual capability question with regards to the volumetric displays. And this comes from the affordance of having a 360-degree viewing angle. The question becomes raised, how do you present text to users when they might be viewing it from any angle? Because just like trying to read a sign from inside a restaurant, it could become difficult because of the orientation issue of how that text is presented. And early on in this investigation, we realized one of the big problems of this orientation effect is an ambiguity problem. That as a word becomes rotated, it becomes hard to understand what it's saying. Okay, so here's the word Bob under different rotations. You can see the letters and the word itself becomes ambiguous. So we looked at two techniques. One was underlining the first letter of each word, which disambiguates at the word level because it's saying the beginning of the word and the bottom of the word. And the other technique was making all the letters capital, which basically disambiguates at the character level because now each individual character is unambiguous with the exception of M and W. So we first ran an experiment with just one user at a time where we presented a word in the volumetric display under different orientations and using the different disambiguation techniques, and the user was asked to read the word as fast as possible and to type it in. And we really wanted here to understand what would the effect of the reading orientation be. So here are the results. We actually looked at two different types of rotations. One was as pitch, which is about the x-axis, sort of an up-down rotation, and one is yaw rotation, about the up-down axis is the yaw rotation. And that's the type of rotation which would naturally occur from walking around the display. And what's interesting here is within a 60-degree interval, we're really not getting a hit on reading times, and it's at the 90-degree level where the reading times really spike. And that's because at 90 degrees, the text actually becomes parallel to your vision. Okay? So you can't even see the text, let alone read it. You need to move your head, be able to see it, and then try to figure out what it says. The other interesting effect that we're seeing here is that the uppercase technique did do significantly better than the underlining cue, okay, which means it is important to disambiguate at the character level. So what we wanted to do is take this data and apply it to a technique. So based on an understanding of the human, try to develop a technique for optimizing the orientation. So we developed an algorithm. The algorithm is for multiple readers. So the idea is if we have some sort of idea of where those readers are, we can find an orientation that's optimized for those readers. So what we do is we take the viewer axes and we take the text axes, and we look at the divergences between each of those principal axes, and based on the times that we got from the previous experiment, which were actually hard-coded into this algorithm, we can estimate what the reading time would be. And then for multiple readers, we do this and we try to find the orientation that minimizes the group reading time averaged across the entire group. So we applied that algorithm and used it in a multiple user experiment where we now had 3 readers sitting around the display. We projected a word onto a cube. You can kind of make out the cube here. And then the cube was rotated in different ways, and the users were all reading the same text at the same time. And we either projected the word just naively and had the orientation updated that way, or we updated it with the orientation algorithm that we developed. So the results here, the x-axis are showing all the different orientation conditions from the experiment. And the y-axis, again, is the reading times. And we see the pink line, the pink solid line, is showing the reading times when the orientation was updated using our algorithm. And again, the significantly reduced reading times across the group. So it's showing it is a technique that can be used when you have multiple people reading text at the same time. The dashed line here is showing what our algorithm would have estimated. And I won't go into the details, but you can see it's underestimating in all cases. But there is a correlation, which is why we are able to find a minimal reading time for the group. So now I want to move to some of the motor capability questions associated with volumetric displays. First is, how are we going to point in these 3D displays? How are we going to select things? We don't even know what a mouse looks like, let alone a cursor, when you need to work in 3D. So one of the most direct approaches is to take our standard mouse, make it wireless, and be able to control it in 3D and have that map to the position of a cursor. So it's kind of like extending where your hand can reach. And when you do this, you basically now have a 3D Fitts law task. So what we actually did was we took the targets, we took the height, the width, and the depth of the target, and we came up with a new three-dimensional Fitts law model, which was able to model movement times when pointing at these 3D targets. I'm not going to go into detail because we've already talked about Fitts law, I think, enough in the first half of this talk. But one of the most important things about this project that we did was not only that we came up with these new models that can be applied not just for volumetric displays, but any 3D environment for pointing, was we also found that the depth of the target, this new dimension, plays just as much role, if not more in some cases, as the other two dimensions. Basically, what this means is the pointing task becomes very hard because you have these 3 dimensions all playing a big role in your movement times. So another technique used for pointing in 3D is called ray casting. This comes from the VR literature, where instead of controlling just a point cursor, you basically cast a virtual ray. It's like shooting a virtual laser pointer through the scene. And the first target that becomes intersected is the one that you select. And this makes pointing easier because you no longer need to specify that 3rd dimension. You just need to point towards the target. But a problem with this technique is that you now have an ambiguity problem, just like you had with the bubble cursor, or with an area cursor, is that multiple targets can be intersected by this ray. And this is actually an existing problem in the VR literature that we wanted to look at when applying this into the volumetric display. So we came up with a bunch of new techniques. The depth ray was the one that's most successful that I'll show. So this is another video, so if I can get the lights down again. The depth ray basically placed a depth marker on the length of the ray, and the user can move their hand forwards and backwards to control the position of that depth marker. So in this is just a little demonstration where the user is trying to select the sphere, and sometimes the user is just demonstrating how the depth marker moves back and forth. You can see here. So the hand moves back and forth, and so does the depth marker. And what the technique does is it selects the target that's closest to the depth marker that is also intersected by the ray. Okay, so that depth marker should not be thought of as a cursor, right? It's just a disambiguation mechanism. Whichever target's closest to that marker will be selected. So really quick forwards or backwards movement can perform that disambiguation.
Cursor. It's in effect a depth bubble cursor, isn't it?
It's actually similar, and we've done some follow-up studies comparing the two. What the depth ray is doing is it's controlling the cursor with 2 dimensions of orientation and then 1 dimension of position. But that 3rd dimension of position isn't an absolute position. It's just whatever's closest to this target. Yeah. So there's follow-up work at the 3D UI conference that compares the two, and it turns out that they are fairly similar. It's just a matter of the visuals that you're giving to the user. So along with developing individual techniques, we also wanted to look at what happens if you want to actually put together a user interface that people can actually use. So to combine various types of interaction techniques, not just selection, so like menus, scroll bars, things like that, into working user interfaces. So with 2004, we developed an exploratory user interface for volumetric displays, where what we did was we placed motion tracking markers on the user's hand. And by doing that, we could mock up the display as being having a touch-sensitive surface. The user could perform gestures on the surface of the display itself to manipulate the application within. And the application we developed was a model building application where you could build up geometric shapes and models using the volumetric display. And we wanted to look at, not just selection, but how do you activate menus? What does a file browser look like? Things like this. So to do menus with touch-sensitive surface, we basically place the menus directly on the surface of the display. You can tap them to access different functionality. This is our file browser. So what we did was we took a 2D file browser but projected it to the surface of the display. The user could rotate it by scrubbing directly on the surface with one hand, and they could use their other hand to tap on the model that they're interested in. They could organize models here, or they could load it into the center of the display. And then once a model was loaded into the center of the display, they could perform all these different types of transformations, the rotation, translation, and scale. And again, these were done with gestures that were directly on the display surface. And then for selection, we implemented the depth ray, but we no longer have an input device with buttons. Okay, and this is a problem with gestural interfaces. So what we did was we just allowed this little sort of shooting gesture with your thumb to say, yes, I want to click and select the target. So that application was just sort of exploring what happens when you have a single user working with the volumetric display. We next wanted to look at what happens when you have multiple users collaborating with the volumetric display. Because as we talked about before, a lot of the affordances are particularly suiting for collaborative interaction. So what we did was we had multiple users. They each had their own input device, which is being tracked in 3D space. We were also tracking where the users were themselves, so we could do things like the text orientation and some other interactions based on where the users were standing. And some really interesting issues come up when you do have multiple people. The one thing is, when you're viewing a model, you're all going to be viewing it from a different perspective. So it's not like everyone in this room looking at this display, we all see the exact same thing. And in 3D, that's a big deal, because in 3D, depending on what you see, you might perceive what you're seeing very differently. So we developed a way to pass viewpoints from one to another. So we called it location-aware rotation. But basically, when you start to rotate, you see a widget indicating your viewpoint, and you see a widget indicating your collaborator's viewpoint. And as you rotate, these widgets rotate with the model, and you can actually snap other people's viewpoints to where you're looking at the model from. And if you release the button, it'll just snap back to the original rotation, but you can also pin it down and work from that area. So it's a really quick way to pass viewpoints from one another if you're seeing something that the other user isn't quite getting. We implemented text flags, so you could actually label different areas of the model and then type in the label. And then the orientation of these labels were being updated using the algorithm that we talked about before. And we also looked at some more advanced features, such as splitting the scene. The reason we did this is because all the techniques that we developed for this application could be used in parallel. Okay? So one user could be labeling text, other user could be rotating, things like that. But in some cases, you're not going to both want to be rotating at the same time, for example, right? Or if one person wants to work on the foot of this model and the other person wants to work on the nose, it'd be hard to do that at the same time if both users wanted to zoom in. So you could split the scene, you each get your own view, do some work, and then merge the work back together. So in summary, with the volumetric displays, we understood the affordances with the display. That led to some interesting human factor questions, such as the depth perception, text readability, and also pointing in 3D. And then we took an understanding of those human factors and developed new interaction techniques, such as selection, but also user interface design, such as for a single user, but also collaborative interaction. So in conclusion, today I've talked to you about designing interactions based on an understanding of the human capabilities. We looked at contemporary technology and talked about the bubble cursor, but we also looked at some more advanced technology with the volumetric display. My future interests have this sort of same branching into contemporary and future technologies. I'd like to continue working with both. So with contemporary technology, I'd like to look at formalizing this interface bottleneck that occurs when using systems, and looking at the better we can understand and model this bottleneck, the better we can understand what is truly efficient and optimal interactions. I'm also really interested in formalizing the sort of bottleneck that occurs within a user, which is a transition between novice usage to expert usage. Because when you use systems, you basically use it the way that was most obvious to use it when you started with that system, where there could be expert ways of working with that system that you might just not be aware of. And I'm really interested in helping users transition between these two usage behaviors. And the other thing I'm really interested in is looking at applying what I've done and adapting it to people of different usage groups. And we talked about at the start of this talk how this framework down here is applicable to different technologies because you're changing the associated capabilities. But similarly, as you change the usage group, such as to a child user or to an older user, again, you're going to be changing what the perceptual motor capabilities are as well. And you actually get into a new capability that I haven't even talked about is what the cognitive capabilities of the user are. And I'd also like to continue the work in the emerging technologies. So there's a lot of interesting work still to be done with the volumetric display. But we have a number of other technologies that I've been working on in the past and interested in working on in the future, such as large high-resolution displays. And also electronic paper is something I'm really interested in and like to begin working in. Because I think displays like this, which are flexible, are going to be ubiquitous in the next 10 or 20 years. And be really interesting to see how that changes the way we think about what paper is. So with that, I'd like to acknowledge the following people. Many of these people were co-authors on the work which I presented today. And I will now take any other questions that you might have. So thank you.
Really, 120 slides?
Yeah.
Yeah, someone once told me a rule of thumb that is they spent 3 minutes per slide or something like that. Good. So fortunately for you guys, I didn't do that. Mm-hmm.
So, for your bubble cursor work, for example,
yep.
You convinced me beyond a shadow of a doubt that it is a more efficient way to select stuff. You had me at your log demo. But it's hard for me to sort of assess what that means in the context of real-world use, or how, generally how important selecting stuff more efficiently is in terms of how my day would go better if I don't know how, I don't have a feel for how much time I spend selecting stuff, and how if I double that efficiency, it would make me happier as a typical user.
Right.
Do you have any either thoughts or just anecdotal evidence of like where it is in the spectrum of using both?
Yeah. So one answer is that it's a huge deal to HCI researchers, right? And a lot of work at Kai and Wis is right. So, I mean, is that an answer that we should be satisfied with? Probably not, right? Another answer is that if you logged how many times you click on things within a day, you'd probably be surprised as how high that is. And I don't actually know of a specific study that has done that, but it would be interesting to look at. The third answer is, let's say I do make selection 10% faster, 20% faster for you, and you finish your work 20 minutes faster because of it. Are you going to be happier? Are you even going to notice or care? And that's another interesting question. I think there's this whole branch of HCI into it's called affective computing that actually looks at the emotions and happiness of a user. And I guess the one question is, should a user interface designer care about that? Well, if you're an employer and you have 200 employees using your software, you probably don't care if your employees are happy, or you care if they're finishing their work faster. But from a perspective of end user software, you do want to make the users as happy as possible. So,
A follow-up to that question is an evaluation of. I mean, the bubble cursor is very busy visually.
Right.
Because you've got this thing moving around, it's big.
Right.
And there's a question: have you actually sort of seen how that looks in context of real world stuff? Yeah, so the answer to that is no, we haven't, and that would also be it's sort of the next step.
I know who would care is the animators. They actually, was it you that talked to me about this?
Yeah, so
There was problems.
Yeah, they would pay cash money for that. Sorry.
Right. And it's a next step of the research is actually applying this in an actual working user interface. Because it's not just the visuals that are going to be different. Or have an impact. It's that there's these subtle issues that are going to come up when you actually are always selecting a target within a user interface that we really need to.
In the case of things like with animators, where every pixel is potential click point.
Yeah, that's the problem.
Yeah.
I mean.
Right. Yeah.
You
Definitely.
don't know what the targets are.
But the idea that the bandwidth required of a task is suited, is designed or controlled in explicit ways that appropriate to the task.
Right.
Something that we're not really doing.
Right.
In our UI, right? We require all sorts of precision where it's not really necessary.
Right. Yeah.
It's coming out in our wrists.
I haven't taken the time to do this, but I'd like to take something like PowerPoint when you're trying to move an object, right? And just show a gradient map of what the hotspots are for just a traditional cursor, because you'll see these tiny little spots for like, scaling, right? And then an entire hotspot dedicated to moving that object, right? To clicking and moving it, right? It's completely disproportionate. And Patrick has done some follow-up work himself on looking at how to change the visuals, so you're not seeing a cursor growing and shrinking.
Another group who's going to be happy about better pointing techniques, which is some designers who really want to make crappy user interface with teeny tiny targets. Give them this technology. Don't encourage them. Oh, is this recorded? I've got another follow-up question to what Ed said. So I was at a talk at Bubble Cursors. Congratulations, has generated a lot of follow-up work, which is great. There was one talk I saw at Kai where they talked about two problems. One that Ed mentioned, which is the flashing of the bubble. But they also talked about some specific scenarios where the bubble cursor does not do well because the visuals clash with what the actual, like the affordance clash with what really happens. You know what I'm talking about?
Are you talking about the paper that was this year?
So what they talked about is the following. There's some scenarios where you've got a huge bubble that suggests that you're almost there, but as you get closer, the bubble shrinks.
Right.
And so, in terms of, I'm kind of curious, did you investigate that scenario?
Yeah.
Do you know what I'm talking about, the scenario? It's when a bunch of targets are lined up.
Right,
In the worst case, they're lined up in a circle. And then, if in the middle of that circle, you've got this huge bubble, as you get closer to the target, the fact that they're adjacent to each other means the bubble shrinks. In the worst case, if you have two immediately adjacent targets, the bubble will...
Yeah, sure.
It's just the problem is that, so if you're coming sideways to a pair of closely adjacent, right, like this, if you're going left there, right, so the closest...
I can see how something like that.
So I'm just wondering, like, we've looked at a couple of scenarios where the affordance is wrong. I mean, there's two things, right? One of them is the question, what is the size of the motor space? And the other is, do users have a good idea of, how much time and precision they need?
Right.
Or could it actually, make them slower if they had this expectation that, well, I'm almost there, and then it keeps, they already reduced their speed to kind of get that, and then it kind of keeps dragging.
Yeah. So I had this other, I had a undergraduate student working on this follow-up project, which never formed, but let me, you might have seen this before, but, so we actually wanted to compare the bubble cursor to this, right? Where it's still bubble cursor selection in motor space, right? But now you have the visual feedback of exactly what the Voronoi targets are. And we did get to the stage of doing some pilot studies, and we just weren't seeing a huge difference. So I think...
Do also with the distribution of the targets and
it could be, and there's probably specific distributions where you have a very bad cognitive model of what. So in this case, where it's just randomly distributed, maybe these regions are kind of regular and uniform. Yeah. Mm-hmm. Yeah.
Did you have a minimum distance between the targets in this case?
In this, I could not tell you exactly. I know we didn't overlap targets. That's all. I'm not sure if we had a minimum. Yeah. Any other questions? Great. Well, thank you very much for coming. Thanks.